Nice.
Lit.
All right. Before we get into some examples here, guys, I just want to give you a general overview of what we're going to talk about. So it'll be pretty quick. So suppose for a second, I want to give you a physical example so that'll kind of put everything we're doing into a framework that hopefully makes sense. So suppose I gave you a velocity function for, I don't know, here's Mr. Carr.
Mr. Carr.
Yeah, this is going to connect to physics. If you've taken physics, this will hopefully make a lot of sense. If you haven't taken physics, it should still make sense. But let's say this car is traveling and its velocity function is, let's say something simple like 3t squared. Okay, so what that would mean is at time 0, his velocity is 0. At time 1, his velocity is 3. At time 2, his velocity is 12, and so on and so forth, right? So his velocity is increasing, right?
So this is about the displacement of the area.
Exactly.
Woo.
So those of you taking physics know that if I graphed his velocity versus time, right, it would look like this, first of all, right? It's a quadratic function. And suppose I was interested in knowing, I don't know, how far does he travel? Alyssa, can you not do that? How far does he travel? So the question we're going to answer is how far you go from, let's say, from time, let's make it from time 1 to time 4. Okay, that's the question I'm going to answer. How far? It's not an easy question, right? Because his speed is changing all the time, right? So it's not obvious how far he would travel. So, so anyway, in physics, what we do is we say, well, here's time 1, here's time 4. And what we say is, well, isn't distance, like displacement, velocity multiplied by time, right? For example, meters per second multiplied by seconds gets you meters, right? And so the argument would be something like, it's kind of a hand-wavy argument at first. You go, well, for that first little morsel of time, you'd multiply his velocity, the velocity is the height of the graph, by the width, the amount of time. And if you repeat that idea over and over again, so you might go, oh, in the first tenth of a second, he would have traveled some tiny distance. And then the next tenth of a second, he would travel some other distance. Long story short, I don't want to belabor this too much because we're actually going to kind of show a more rigorous argument for why this is true later. But this area, right? Think about the area. What's the area? Well, isn't it velocity multiplied by time? So this area here tells you the displacement. So I'll say area is equal to the answer to this question. Are there any questions yet on what I'm talking about? Okay, so that may or may not sit well in your mind, but for now, let's just maybe take my word for it. If you're still unsure, that's just good. That means you're a skeptical person. That's good to be. But just be like, okay, just take my word for it. This area is going to be telling us the distance. Okay, but then you go, well, that's kind of a difficult area to find. Maybe I could estimate it by breaking it up into little triangles and squares or something. But how else could you do it? Forget the area. If I give you a velocity function and you want to know something about the displacement, what's all you got to do? It's the antiderivative, the integral. So, so one way to approach this would be to say, well, I can actually get the distance function. Okay, and so the distance function for this would be t cubed plus a constant, right? Make sense? Let me actually write it like this. It would be x of t. So you guys still with me here?
Mm-hmm.
And then all you'd have to do is go, well, the displacement I don't know why I didn't write delta x, I don't know. But anyway, the displacement would be the position at time 4 minus the position at time 1, right? So what would that be? x of 4 would be 64 plus our constant. And then our position at time 1 would be 1 plus that same constant, giving us, now here's a big idea. What happens to the c? He's cancely wancely. So that what that tells you is it doesn't matter what that c was. It doesn't affect the answer. If I just want to know how far did he travel, does it matter if he started at position 1,000 or position 1,000,000? Like, no, like where he starts, like if he's on a number line, it doesn't matter if he started here, if he started here. In either case, he's going to travel 63 meters. So some notation then. I'm almost done, I promise. Okay, some notation. Well, where did this come from? Where did x come from? Well, it was the integral of this. So what we just did, this is the new notation, is we did the integral of the velocity function. We integrated it. And then how about the 4 and the 1? So when they put a 1, they put a 1 and a 4 on the integral bar, what that's telling you, and if you look at your problem set, that's what we're doing in these first couple questions. What that's telling you is, get rid of this. What that's telling you to do is integrate the function. So in this case, it would be t cubed. So integrate the velocity function to get the position function, and then plug in 1 and 4 and subtract them. Notice there's no c in this because we know it would cancel out anyway, so we don't need to consider it. So in the black here was me showing you how do you tackle this problem with our old methods, right? That's the old method. Still valid, it's 100% valid, but this is a more concise notation. So when you see this, it embeds all that information of like, okay, take the integral, plug in 1 and 4, and then subtract the. Is that a good one?
Yeah, that was a good one.
All right, are there any questions? Yes.
Just a side question comment. So when you said like the range doesn't matter, right? Like where your starting stopping place is, the 1 and your 4, then is that like your like like almost like the limit of which x can be, kind of? Does that make sense? Like it's like I don't know.
Like you're talking about this, right?
Yeah, so that you said it doesn't like matter like where it starts in the number line, correct? Like whatever value it is. But then we went on to the integral where the 1 and the 4 is that like kind of like your.
The 1 and the 4 was just from the statement of the problem. So
Okay.
if I had wanted to know how far did he travel between say time 2 and time 5, there'd be a 2 there and a 5 there, and I'd be plugging in a 5 and a 2 into my thing.
Okay.
As far as not mattering where it started, all I'm saying there was, suppose this guy had started at position 500. So say, he's on a number line, and he started at 500. Well, what the math shows us here is that between time 1 and time 4, well, for example, at time 0, he would have been at 500. At time 1, he would have been at 501. And at time 4, he would have been at 564. Does that make sense?
Yes.
Now that 500 was arbitrary. He could have started at 900, and the numbers would have worked out the same. That's why C is canceling out here.
Okay, that makes sense.
Because it doesn't matter. All we're caring about is how much position did he gain or lose. We don't care where he started. That makes sense. Yes, Kate.
Why is it subtraction when the numbers are on the integral?
Is a good question. Like that. So then that would be I guess that raises another question. Why do we subtract here? Because if you want a displacement, you have to subtract your final position. You have to subtract final position minus initial position.
Mhm.
And so, right. I mean, it's completely not obvious at all. Why would you, like, suppose you buy that, oh, you're going to integrate this and then plug these two numbers in. Well, why subtract them? Why not add them or why not multiply them? Well, the reason you're subtracting them has to do with like this example of displacement. It makes sense to subtract the two position values. Does that make sense?
That's where the physics comes in.
Yeah. But I will show you there's a way. I don't want to do it now because I feel like I don't want to overload you guys with info, but we're going to show in a more rigorous way why this just works for any function. Like how come if you take the integral, plug in these two numbers and subtract the results, why does that always give you the area under the curve between those two numbers? But hopefully this velocity position example at least gives you some insight into why is that. This is the easiest physical example. It's not very, when you start getting into more abstract functions, it becomes a little confusing, like how come that integral gives us the area. But anyway, let's get into some examples. If you're confused right now, like super confused, my advice would be, again, the Richard Feynman. Well, apparently that's like it's like, what's the word when it's like ascribed to him? But actually someone else said it. Shut up and calculate is what I was trying to say. Shut up and calculate is. But he or someone else, well, it's a famous saying when you're learning quantum mechanics, because when that stuff is bigly confusing, so sometimes we're like, just do the calculations and don't try to think too hard about
Don't.
stuff.
Yeah, don't try to think too hard about who said that, JL.
About who said it?
Yeah.
No, it's one of those sayings
No,
where it's
no,
like,
I know what you're talking about. Where somebody else said it and then they took credit for it and everyone can, attributes it to that person, but it's not actually them.
yeah. Not that he took credit, it was more just like, everyone's like, oh yeah, Feynman said that. And then it's like, oh, actually, if you look into it, like, yeah, he didn't say that, it was someone else. But
Yeah.
Feynman's a famous
It's like the
Physicist.
renegade dance.
renegade. Exactly,
Yeah.
yeah.
Yeah,
That's a good example.
great.
That is a good example. Although
Yeah.
Charlie DeMillo really did the renegade dance, she just wasn't the first.
Exactly. Yeah.
Anyways, let's do an example. So, this first one.
Lamau.
Lamau. Okay, so what I mean when I say shut up and calculate is not to say never think about it. It's if you're getting overwhelmed, maybe just do it first and then understand it later. That's sometimes how things go. So okay, so what you do here? Watch, it's very simple. What's the integral of x squared?
1 over.
1/3 x cubed.
X cubed.
Did it backwards.
Okay, so you integrate this, and then you put this little evaluation bar. That bar just means we're going to be plugging in these two numbers. Okay, everyone fine with that?
Mm-hmm.
And so what we get is 1/3 times 3 cubed minus 1/3 times 1 cubed, which is going to give us, let's see, 1/3 of 27 is 9, and 1/3 of 1 is 1/3. So that's 27 thirds minus 1/3, so the answer is 26 thirds. Now the interesting part is that's now that number, it's not a particularly pretty number or anything, but this number is the area. So if you graph a parabola, there's a parabola, and you say how much area is bounded under that curve from 1 to 3. That's the 1. The 1 and the 3 is between 1 and 3. You guys see what I'm talking about? This like kind of irregular looking shape.
Yep.
Looks almost like a trapezoid. There's a hint of things to come. That's actually a method we're going to study is how do you approximate an area using trapezoids or rectangles. But do you guys feel okay about that?
Yeah.
Okay, we're going to do a whole bunch together. So let's do the second one. From -1 to 1, x cubed. All right, step 1, integrate him. It's 1/4 x to the 4th. And then we're going to plug in -1 and +1. Okay. So plug in 1. What happens when you plug in 1? What do you get? 1/4 minus. What happens when you plug in -1?
1/4.
You get 1/4 again. So what's the answer?
0.
0. Now that kind of flies in the face of, something when you study geometry, a lot of times you for good reason. You say, oh, area can't be negative, right? If you're calculating the area of a polygon, it almost never makes sense to say that's a negative area. But in this case, you can have negative area. So what were we doing? Well, look at the original. Here's another thing to keep in mind. What am I graphing? Am I graphing the integrated version, or am I graphing the original function? The original function. So the original function was a cubic. Okay.
Oh,
Now look at the area. So it's area bounded between the curve and the x-axis. So here's 1, here's -1, and look at the areas. Well, first of all, by symmetry. And this all ties back to the whole velocity thing. If this was a velocity graph, then this is negative velocity, meaning you'd be traveling backward, thus taking away from your overall displacement, subtracting from it. So this area, so area above the x-axis, so if you are area above the x-axis, you are positive area. You can be thought of as positive area. So in this calculation, it's like, well, this 1/4 sort of kind of is talking about, well, not actually is talking about this area. And the fact that we're subtracting a positive number means this basically got taken away. So the area below the x-axis is negative area. Here's a good chance for some thinky winkies. So there's something here about, you guys might remember studying even and odd functions, maybe slightly. So this is an odd function, right? Odd functions exhibit a certain kind of symmetry. So there's going to be, we can probably make a theorem about taking integrals of odd functions over symmetrical intervals.
Yeah.
Right? So if we know you're an odd function, doesn't matter how wiggly you are, you can reason out by symmetry that if the integral is symmetrical, then you're probably going to get 0 as your area. Let's keep going. Gonna make it, Bailey. It's torturous, I know. Okay. Let's actually go straight down to D, because that's a good, we'll do C as well, but look at D right below this one. It's almost the exact same function, but shifted up 1 unit. So how will that affect things? Did you see me conserve marker there? It's pretty good stuff, right? Where's my Wokest Green award, please?
Be green.
Be green.
Be
Be
green.
green, sorry.
Once you learn the name of it, maybe.
Yeah, at the start.
That is a good start. The journey of 1,000 miles.
Yeah.
Okay. How does this change things? Well, yeah, so think visually, the whole function is shifted up 1 unit. So think about what that's going to do area-wise. By the way, I'm going to skip to the end real quick and graph it. Because now the graph looks like this, right? Where this is 1, this is 1, and this is 1. Does that make sense? When you shift it up 1, now the x-intercept is -1. And so my area is now going to be all positive. So we should expect to get, now that's a weird looking shape, isn't it?
Yeah.
What will be the area? Any guess? Any guesses?
1/2. 2.
It's not 0, right?
1/2.
1/2. All right, let's see what happens. So take the integral. here's the best thing is a lot of these have really, not all of them, but many of them have kind of like very interesting lines of reasoning you can take to figure out the answer. But if you're having trouble with that, it's fine. You can just calculate. So your calculation would be 1/4 x to the 4th plus x. Integral of 1 is x, right? And then we're evaluating from -1 to 1. So all you got to do is you plug in 1. Parentheses can be helpful here. So plug in 1. And you get, you don't have to show this every time, guys. Just so you, that's me plugging in 1 at 5/4. So in practice, you can just go straight to 5/4. And then subtract. Now I'm going to plug -1 in. Everyone okay with that? Now here's the interesting part is, so plugging in 1 to this function gives me 5/4. And plugging in -1, let's see, what do we get here? We get +1/4 plus -1. So that's -3/4. So what's 5/4 minus -3/4? 2. Which I think is kind of a neato answer. This weird wiggly shape. By the way, think of the 2. I mean, how wide is, this interval is too wide, and we raise it up 1, so a 2x1 rectangle of area has an area of 2, excuse me. How do we feel? How are our feelies? Yes, Aiden?
What units would you be working with? Would it just be units then?
It would be, I guess, technically square units. Don't worry about units. This is where, when we get to there's some word problems in here for us to practice this, but like, suppose this was a velocity function in, say, feet per minute. If this was feet per minute, then my answer would be feet. Let's suppose this was like a volumetric flow rate, like gallons per second, then my answer would be in gallons. Don't worry, Lillian. We only got 18 more minutes.
That's reassuring.
That's reassuring. Okay. Let's do, yes. I did. Let's do it.
Yes.
You guys, would more examples be helpful? Do you guys want to keep doing them together?
Yeah.
If you feel like you totally got it and you want to just tune me out and do them on your own, it's not going to hurt my feelings. I mean,
You got it.
No, you definitely don't.
Oops,
Okay,
sorry,
let's-
J-Ho.
I figured we did, at the very minimum, complete the whole first page together. Just so we're not
This one
confused. So C looks like this. So 2x minus 1. Okay. Let's take the. I think I'm going to graph it first. Actually, I think as I do with a lot of stuff, I like to start with a graph and then kind of just see what kind of answer am I expecting to have. That makes sense.
Yeah.
So it's sort of like this. We're going from -1 all the way over to 3. So I can see I'm getting some negative area. That's all negative area. And I'm getting some positive area. So now I didn't graph it like super carefully, but I just know I'm expecting some number that's like not very big. Could be positive, could be negative, I'm not really sure. I do know that this is 1/2, and there's more space between 1/2 and 3 than there is between 1/2 and -1. So I think it's going to be positive. I think this positive triangle has more width to it. So anyway, what's the integral of him?
X squared minus
X squared, and this guy's going to be x. So our integral is x squared minus x, and then we're just going to plug in -1 and 3. Okay, let's just be careful here. Plug in 3. 9 minus 3 is 6. Now let's plug in -1. Be extra careful there. -1 squared minus -1 makes 2. So, everyone okay with that? There's certainly no shame in doing this, guys. In my opinion, though, this actually, for me personally, would make me more prone to making a mistake. I think I'm probably more reliable just plugging this in mentally. But anyway, 4. Turns out that's the area is 4. Beautiful. E. So let's see. E. Okay, we're going from 1 to 4 on the old square root function. So, this is x to the 1/2 power. So what's the integral?
2/3 x.
Yep, 2/3 x to the 3/2 power. Is everyone fine with that?
Yeah.
No questions? Questionings? Okay, going from 1 to 4. Okay. It's gonna get ugly. So 4, so I'm actually gonna write it out this time just for. If you're taking the AP exam, you take that test, you'd actually just leave your answer like this. You're done. But
Why?
we're civilized here, so we're gonna.
Wait, but why?
It's just a weird policy. I don't know. I guess the spirit of it is they just want. They don't really want. They're really strict on like. If you look at the points, the way the points are awarded, it's like, oh, there's a point for those free response ones. A lot of times, it's like you're setting up the integral, so you get a point for setting it up correctly, and then you have a point for integrating correctly, and then like there's a point for the final answer. And I guess they didn't want the focus to be on. Can you calculate that the arithmetic, right? They wanted to make sure the points are awarded for the calculus and stuff.
And will we go over all these weird rules closer? Okay, great. Quit, lit.
I like to just.
Lit.
I mean, I try to make this class just like a Calc 1 class, university class, basically. Although there's a couple things we cover that probably wouldn't be in a typical Calc 1 class, but they're on the AP exam, so we cover them. And then at the end of the year, I'll help you prepare practice tests and stuff.
Sounds good.
Okay. What is 4 to the 3/2 power? It is 8, right? You square root, because the 2 means square root. Square root of 4 is 2, and then you cube it, you get 8. 8 times 2/3 is 16/3. And then this is a little bit easier. It's just 2/3. And so the answer is 14/3. And then we, of course, what did we just calculate there? Well, we just calculated the area bounded by this function. The area bounded under this function between 1 and 4. So it's kind of like weird looking. Looks like a rectangle that got kind of. What's that technique with wood where it's like a little, like you shave it off?
Lathing.
Lathing.
Or,
Even if it's like the handheld one. I know it doesn't
What's a
lathing go
planing?
spinny.
planing.
Planing. That's what I was thinking of. It's like a cheese,
Lesser.
or is it a cheese
File.
grater if it's slicing out a slice?
That's my argument, so I call it cheese lesser.
That's not what I, no.
That's not where you're going.
I thought, no, grating makes it into tiny little cheese pieces. The other thing slices off like a big sheet. Cheese. No, but not slice. So I know and there's a cheese slicer, slices it cross sectional, but there's another one just like shaves off a. That's also cheese grater?
Well, I was just
Why did you start this
so you
argument?
can get the spinning.
Why?
Why have you done this one?
I apologize. Mr. Coleman would know the answer to this.
He would.
He's
There would be no dispute.
a true ratatouille.
Mix it like wavy cheese.
Wavy cheese?
That's a Norwegian thing.
Norwegian thing.
Wavy cheese.
That's
All right.
fantastic. Are they like curly cues?
F.
No, just wavy.
I got weird answer.
You did?
Yeah, I don't know what I did. I got a pause on that.
Well, it's good you caught that. So for F, guys, again, I'm going to graph it first to get a sense of what answer am I expecting. So hopefully this is a graph that so it's a shifted down parabola, and then you can hopefully it's fairly obvious that this guy's going to cross the x-axis at 2 and at -2, which just so happens to be the bounds of the integral. So the area trapped between this function and the x-axis is all down here. So what kind of area is all that? It's all negative. Okay. And so what that tells us is when those numbers get plugged in, like we should be expecting probably it to be like a negative minus a positive. So let's just get the calculation. So the calculation goes 1/3 x cubed minus 4x evaluated from -2 to 2. So plugging in 2, so remember you got to plug 2 into the whole thing. So that's going to get us 8/3 minus 8. So that's what we get when we plug in the 2.
-16.
And when we plug in the -2, you get -8/3 plus 8. As you can see with this stuff, you got to be like ultra careful with your negative signs.
Yeah, that's where I messed.
Yeah, it is like extremely easy to drop a negative or flip a negative. It's like happens all the time.
Mr. Hall,
Yes.
from right there, can you just take the 8 out of parentheses and just subtract and get -6?
No, because
Well-
it makes it negative.
Yeah, because this, hold on. You have -8 minus 8, that's -16. I think it's easier personally just to turn this into that, and then this is just the opposite of that, so -16/3 minus 16/3 is -32/3. Yes.
Hold on.
So there's the benefit of graphing beyond just, I mean, I think graphing actually helps you understand what the heck you're doing, but it also helps you avoid a mistake, right? If you graph it, then you know for sure. That's what I like what you said there. We were like, well, I calculated, but I know the answer's wrong. That's like one of the best things you can learn in math. It's like, how do you know when your answer's wrong? So, let us do one or two more.
Now about time for one.
Time for what?
One looks like
One.
one.
Okali. Let's do one that's a little. Let's maybe pick one that's a little bit weirder. I do want to do a backward one.
What do you mean?
Well, number 3 says sometimes the bounds on the integral are backward. Yeah, I'll show you. They're easy. I'll show you how to do them. They look weird. They do come up sometimes.
Do they just end up like really negative or something?
Yeah, well, let's just do one of those to start. Let's do I don't know, B, I guess. 3B. So 3B is so let's graph it first. Although when you graph this one, it's a little strange because you go, well, I know how to graph square root of x, and I know how to go from 1 to 9, but so maybe you can make a conjecture. I don't know. If we know that if we took the area from 1 to 9, it would give us a positive number. So what's going to happen when we just reverse those bounds? Let's see. So the integral of x, the square root of x is 2/3 times x to the 3/2. And we evaluate from 9 to 1. When you plug in 1, you get 2/3. And when you plug in 9, let's say we do it all in our head. Let's plug in 9. So square root it, 3, cube that, 27. A third of 27 is 9. 9 times 2 is 18. Cool beans? So let's think about this. I mean, if the bounds had been 1 to 9, those would have been flip-flopped, right? It would have been 18 minus 2/3. So as you can see, the moral of the story here is all that ends up happening is you just get the opposite of what the answer would have been. So 18, what is that, 54?
52 negative.
Yeah, negative 52/3. So what's this area? This area is positive 52/3. So if you just go backward on the integral, you get the opposite answer. I'll spare you for now. Later on, we'll see why would you want to do that? What's the point of reversing? Long story short, is if you want to go backward in time, if you want to if you have a system, if you have an evolving system, you want to look forward, what's going to be the state of the system later? You want to take an integral. If you want to say what was the state of the system earlier, you can go backwards. We'll go over plenty of examples of that. All righty.